At 5:58 a.m. on May 26, 2025, a Ukrainian MiG-29, once a standard Soviet fighter, crossed into Russian airspace on a mission no one thought possible. Its target, the FSB headquarters in Belgorod, the core of Russia's security apparatus, protected by some of the world's most advanced air defenses. This was not just another sortie. It marked the first time Ukrainian forces attempted a direct strike on an FSB facility, transforming a theoretical challenge into a historic first. Engineers had retrofitted the aging jet with French AASM Hammer bombs, a GPS antenna, and an iPad taped to the cockpit, solutions that defied conventional expectations. The result was a precision strike platform assembled with battlefield improvisation. But how did a Cold War-era aircraft become capable of such a modern attack? The impossible mission: how a MiG-29 became a precision strike platform. Transforming the MiG-29 into a platform for modern precision-guided munitions demanded more than routine modification. It called for a complete reimagining of what the aircraft could do under pressure. The mission's urgency was clear. The FSB headquarters in Belgorod was a target few believed could be reached, let alone struck with accuracy. Engineers in Kiev, working under strict wartime deadlines and persistent threat of attack, set about the task with limited resources. Their solution began with the fundamentals, making it physically possible for the MiG-29 to carry the French AASM Hammer bombs, a weapon system never intended for this jet. Custom pylons were fabricated in local workshops to mount the bombs, each component tailored by hand. The process was far from straightforward. Access panels originally designed for Soviet-era munitions had to be opened and reconfigured. Power cables were routed through these tight spaces, adapting the MiG's electrical output to meet the demands of Western electronics. The urgency of the work left no margin for error and no time for second attempts. Every modification was performed with the knowledge that failure could mean disaster, not just for the mission, but for the pilot and the engineers themselves. The technical gap between the MiG-29's analog avionics and the digital requirements of the AASM Hammer bombs was the next major obstacle. The jet's original systems, built in the 1980s, were incapable of processing or transmitting the GPS and inertial targeting data the French bombs required. Rather than attempt a full-scale avionics overhaul, the team turned to an improvised digital bridge, an iPad, taped directly to the cockpit console. This commercial tablet ran custom software that translated Western targeting data into signals the bombs could understand, effectively serving as a digital interpreter between incompatible worlds. The iPad's connection to the bombs was held together with zip ties and battlefield ingenuity, a jury-rigged solution that became the heart of the mission. Integrating GPS guidance brought further complications. The MiG's airframe, never designed for satellite navigation, needed a new way to receive global positioning data. Engineers mounted external GPS antennas to the forward mounting points, connecting them to the iPad. These antennas relayed real-time satellite data, which was then processed by the tablet and fed to the bombs. The entire system had to withstand the stresses of flight: vibration, abrupt maneuvers, and rapid altitude changes, without losing its fragile connections. The result was a network of modern electronics and legacy hardware, operating in unison under conditions none of the original designers could have anticipated. The stakes were amplified by the scale and power of the MiG-29 itself. At takeoff, its two Klimov RD-33 engines generated more than 18,000 pounds of thrust, propelling the aircraft and its untested payload into the sky. The pilot, strapped into a cockpit crowded with both original Soviet controls and new digital components, faced not only the physical demands of flying, but the mental strain of managing a system cobbled together from disparate technologies. Military analysts questioned whether the aircraft would remain stable with its new loadout, and even those closest to the project understood that every wire and software patch represented a potential point of failure. Skepticism lingered in every stage of preparation. The pilot had to trust both the improvisation of the engineers and the reliability of commercial electronics never meant for combat. The entire system was unproven in live conditions, and the risks were magnified by the mission's strategic importance. The transformation of the MiG-29 from a Cold War relic to a precision strike platform was a testament to resourcefulness under constraint. But the technical achievement was only part of the challenge. The pilot would have to navigate through hostile airspace, relying on this hybrid of old and new, and reach the target undetected. With the modifications complete and the aircraft armed, the next phase would test not only the machine, but the tactics and nerve of its operator. The MiG-29 would need to fly at the lowest possible altitude, threading a narrow corridor beneath the reach of Russian radar, where every second brought new risks. A flight through shadows, low-level tactics to evade the S-400. Staying undetected required more than just technical innovation. It demanded a flight profile that left little room for error. The MiG-29 pressed forward at a steady 50 meters above the ground, its passage bending wheat fields and scattering birds in its wake. This ultra-low altitude was not just for show. It was a calculated maneuver that reduced the radar horizon to 25 kilometers, exploiting the limits of Russian detection systems. The S-400's radars, powerful as they are, depend on line of sight, and the curvature of the Earth sharply curtailed their reach at such a low approach. The pilot's workload intensified with each kilometer. Navigating at 50 meters, every detail in the landscape became significant. A sudden flock of birds, startled by the roar of the engines, could betray the jet's presence to ground observers, while even minor course adjustments were critical to avoid unexpected obstacles. The pilot's focus was absolute. The margin for error was measured in seconds. Visual detection by local forces remained a risk, but the primary threat was always the S-400's radar net. By maintaining speed and altitude, the MiG-29 stayed hidden until the last possible moment, using the terrain as a shield. The S-400 system, with its 92 N6 Gravestone radar and 48 N6 missiles, is optimized for tracking and engaging high-flying targets. It can monitor hundreds of objects simultaneously across the vast distances, but its effectiveness diminishes against aircraft hugging the ground. The MiG-29's low-level tactics forced the S-400 to operate within its weakest parameters. Even if the radar detected the jet as it closed within 25 kilometers, the system required about 10 seconds to process, lock on, and initiate a missile launch. At a speed nearing 900 kilometers per hour, the MiG covered a significant portion of that distance before the S-400 could react. Terrain masking was not the only challenge. The pilot had to read the ground ahead, anticipating changes in elevation and the unpredictable behavior of wind currents. Weather conditions, such as sudden gusts or thermals, added complexity to the already demanding flight. Each maneuver was calculated to keep the jet below the radar horizon while avoiding inadvertent exposure. The environment was dynamic, with the pilot constantly adjusting for both natural and man-made obstacles. The need for precision was relentless, as a single miscalculation could result in mission failure or loss of the aircraft. As the MiG-29 approached the target area, the tactics that had kept it concealed would soon reach their limit. The next phase required a dramatic change, one that would expose the jet to the full attention of Russian defenses. To deliver its payload accurately, the pilot would have to initiate a steep climb, ascending rapidly to 5,000 meters. This maneuver would subject the pilot to forces approaching 7 Gs, a test of both physical endurance and composure under pressure. The climb was brief but critical, trading the relative safety of low-level flight for a window of vulnerability at altitude. The transition from ground-hugging flight to a sudden vertical surge was a calculated risk. Every second of exposure increased the likelihood of detection and engagement by the S-400. Yet, This was the only way to achieve the trajectory needed for the bomb's release. The mission now reached its pivotal point, where the next move would decide success or failure. The MiG-29's sudden climb was not the end, but the beginning of a maneuver that combined old tactics with new technology. A move that would challenge both physics and the limits of Russian air defense. The toss bombing gambit, defying physics and Russian defenses. The toss bombing maneuver, drawn from Cold War doctrine and adapted for this mission, put both pilot and aircraft at the edge of survivability. As the MiG-29 leveled off after its low-level approach, the pilot initiated a steep climb, pulling the stick back and feeling the cockpit explode with radar warning tones. At 5,000 meters, the jet became a clear target, its presence lighting up Russian screens across the region. The pilot had a narrow 45-second window from the moment of detection to the point of maximum vulnerability, as described by S-400 operator Smirnov. Every second counted. The climb had to be executed with precision, and the release point calculated in advance to minimize exposure. At the apex, the pilot triggered the bomb release. The AASM Hammers detached in a steep upward arc, their trajectory calculated to maximize range without requiring the MiG to overfly the target. This maneuver, originally designed for nuclear delivery, allowed the aircraft to drop its payload from a distance while immediately breaking away. As the bombs left the pylons, their solid rocket motors ignited, burning for 15 seconds and accelerating each bomb to Mach 0.8. This rapid boost was critical. Not only did it extend the bomb's reach, but it also complicated any attempt at interception. The MiG-29 immediately nosed over, diving back toward the ground to escape. The descent was abrupt and violent, with the pilot using sharp changes in altitude and direction to evade tracking. S-400 operators, aware of the threat, launched two 48 N6 interceptor missiles. These missiles, designed for high-altitude targets, struggled to adapt to the MiG's abrupt dive and the cluttered radar returns from the terrain below. The first missile lost lock as the jet disappeared into ground clutter. The second, guided by the last known trajectory, closed in, but was ultimately defeated by the MiG's unpredictable flight path and rapid descent. While the jet evaded, the AASM Hammers continued on their programmed course. Their guidance systems, combining military-grade GPS receivers and ring laser gyroscopes, enabled the bombs to navigate independently even if GPS jamming was attempted. The inertial navigation system, hardened against electronic interference, could steer the bomb within 10 meters of its target using only internal memory and motion sensors. The bomb's rocket-assisted speed and compact design further reduced their radar cross-section. Their near-vertical dive toward the target cut the S-400's interception probability from an estimated 85% for conventional munitions to just 12%. Russian operators tracked the bombs, but the geometry of the attack and the bomb's minimal radar signature left little time for an effective response. The AASM Hammer's tail sections, equipped with control surfaces capable of adjusting 50 times per second, made constant corrections during flight. These micro-adjustments, guided by the onboard navigation suite, enabled the bombs to maintain a precise course even during the final moments of descent. The near supersonic terminal speed and steep dive angle meant that, as the bombs approached their target, interceptor missiles passed within 200 meters, but failed to achieve a kill. The entire sequence, from the start of the climb to bomb impact, was measured in seconds. The pilot's exposure to enemy radar was brief but intense, and the margin for error was minimal. The success of the toss bombing gambit rested on the synchronization of timing, altitude, and release, each variable calculated to maximize survivability and strike accuracy. The MiG-29's modifications, the pilot's training, and the AASM Hammer's design all converged in this moment. As the MiG disappeared below the radar horizon, the bombs continued their descent, locked on their target. The S-400, designed to defend against the most advanced threats, had been outmaneuvered by a combination of old tactics and new technology. The next few seconds would determine the outcome, not just for the mission, but for the intelligence hub at the heart of Belgorod. Shattering the untouchable, the bombs that changed everything. 2 bombs, separated by just 0.3 seconds, shattered the illusion of invulnerability that surrounded one of Russia's most secure intelligence facilities. The AASM Hammer munitions, engineered for surgical precision, brought together advanced guidance, a powerful solid rocket motor, and agile control surfaces. Their design reflected a shift in modern warfare, the ability to strike high-value targets with accuracy while minimizing collateral damage. In this mission, the bomb's technical sophistication and the tactics behind their delivery converged to devastating effect. Each AASM Hammer relied on a dual-layer guidance system. Military-grade GPS receivers paired with a ring laser gyroscope-based inertial navigation package. This unjammable combination allowed the bomb to maintain its course even if electronic interference disrupted satellite signals. The inertial system alone could keep the bomb within 10 meters of its intended coordinates. The solid rocket motor, igniting at release, burned for 15 seconds and accelerated the bomb to Mach 0.8, extending its reach and making interception far more difficult. At the tail, control surfaces adjusted course 50 times per second, ensuring the bomb responded instantly to changing flight conditions and maintained a steep, precise trajectory toward the target. As the bombs entered their terminal phase, their radar proximity fuses detected the rooftop of the FSB headquarters approaching at 250 meters per second. The detonation sequence was programmed with a 0.025 second delay, a detail that reflected meticulous engineering. This delay ensured the warhead would explode at the optimal depth inside the building, maximizing destructive potential. The first bomb's high explosive charge produced a jet of molten copper, designed to slice through layers of steel and concrete. Just 0.3 seconds later, the second bomb struck 20 meters away, targeting a structurally weakened section and compounding the damage. The aftermath unfolded with brutal efficiency. The confined architecture of the FSB headquarters amplified the force of the explosions through reflected overpressure. Blast waves ricocheted between concrete floors and steel supports, multiplying intensity with each rebound. The initial detonation fractured the building's core, and the follow-up strike exploited these weaknesses, accelerating the collapse. Within 5 seconds, a 5-story structure that had housed critical intelligence operations was reduced to rubble. The shock was immediate. Local air raid crews barely had time to register the strike before the building's interior was obliterated, servers and documents buried beneath tons of debris. The magnitude of destruction was not the result of brute force alone, but of deliberate engineering and tactical innovation. The bomb's precision and the timing of their impact demonstrated a mastery of both technology and operational planning. Ukrainian forces had taken a retrofitted MiG-29, armed it with French-made precision munitions, and executed a strike that bypassed one of the world's most advanced air defense networks. The operation combined old hardware with new tactics, proving that ingenuity could overcome even the most daunting obstacles. This action did more than destroy a building. It sent a message about the changing nature of warfare. The use of precision-guided munitions in a high-risk, high-reward mission highlighted the growing importance of adaptability, creative problem-solving, and the willingness to take calculated risks. The collapse of the Belgorod FSB headquarters was a moment where technical innovation, tactical daring, and human resolve intersected. As the dust settled over Belgorod, the implications of this strike began to take shape. The mission's success was not simply a matter of military hardware, but of the ingenuity and determination that drove every stage of its execution. The story of this operation raises questions about how future conflicts will be shaped, not only by technology, but by the people who find ways to use it under pressure. The strike on Belgorod's FSB headquarters underscored how battlefield innovation can redefine the balance of power. Ukrainian forces took a MiG-29, an iPad, and zip ties, tools never meant to work together, and turned them into a precision strike system capable of breaching one of Russia's most heavily defended sites. This operation highlighted the effectiveness of asymmetric tactics, where creativity and adaptation can outmaneuver technological superiority. Adaptability proved to be the ultimate weapon. If you found this mission as astonishing as we did, hit subscribe for more deep dives into modern warfare.